How are we all doing today? So, what we're going to be looking at today is kind of going back to the world of forces, but we're looking at them in a rotating sense, but not for torque. We're looking at traditional forces, like an F equals ma idea from Newton's second law, but we're going to be doing this when the object itself is moving in a circular path. So here I have a foxtail. They used to be made by Klutz years ago, but they stopped making them. They couldn't sell them very well. They went back to Cassidy Labs, and it's really just a ball with this long nylon streamer at the end of it. I used to play with these all the time as a kid. Got it from my cousin. It was awesome. We've got two of them now hanging around here. And if I take something like this, a foxtail, and I just start to spin it, you can see that at any point, the nylon streamer here has some tension in it. And if you take, a lanyard and you spin it around, or a rope with a grappling hook at the end of it because you're trying to be Batman in the middle of the night, whatever. That rope, that line, that lanyard, this nylon streamer here, there's some tension in this as the object is spinning around, okay? Now, as it's spinning around here, that tension is actually what is causing this object to move in a circular motion. Because if I'm spinning the foxtail and then I just let go of it at some point, it's no longer going to be moving in a circle. It's going to get thrown across my room. So what's going on there? How can we think about this? So when we think about this centripetal force, and a centripetal is different than a centrifugal force. This is a pedal here, centripetal force. A centrifugal force is kind of like an imaginary force, they say. It is a real thing, but you have to be rotating in order for yourself to see it. In our case here, we're not rotating. We're watching the object rotate, so it's a centripetal or an inward acting force. And what's happening here is as the foxtail, let's like draw a little foxtail right here, and let's draw a little streamer. So here's the purple streamer. That's the streamer coming back into the center. As it's moving around in a circular motion, there is a tension here pulling back in on it. And that tension pulling back in is what's keeping the foxtail in its track, in its circle. Because whenever we're here, this tension's still pulling it back in. The foxtail wants to go in a straight line. The foxtail wants to go tangent, a tangential or a linear velocity. The foxtail wants to do this, but it's being pulled back in. And when it's being pulled back in, that means it's hugging this circular arc. What this also means is that if you're spinning something like this, and let's say I wanted it to go straight upwards towards the ceiling, where would the ball be when I let go of it? Well, a lot of people think that if I want it to go up, then the ball should be at the top, because that's up, right? But this is a really bad idea. If this is spinning like this, then if we take a look at it, when the ball is at its upward position, it's actually moving this way into my window. If I want the ball to go up, I actually need to release it when it's right here, because the tangential velocity to this point is directly upward. This is kind of counterintuitive because our eyes can't really pick up, if I'm spinning this very, very fast, where the ball is. But think of it this way. If you're throwing a baseball to someone and you want to throw the ball forward, you don't throw the ball when your arm is like this. If your arm is here and then you let go, the ball's going straight into the ground. It's going nowhere. You release that ball when it's here, and you actually release it a little bit on an upward trajectory so you can get that nice arc and reach them. If you want to throw that ball just perfectly flat and straight, that ball is coming out like this. You're up here at that top point, because if you think about it coming over the top, that's the straight point to launch it. So it's kind of a weird thing to think about, but at any given point on the sphere, your linear velocity is always tangent to the curve. Okay, but it is this centripetal force, this tension, acting inward to keep that motion. Now, since this is a force acting in, we can just go ahead and use our classic F equals ma equation. And remember, this is actually a sum of forces here, many forces added together, and the centripetal force can be many forces added together here. We have a few things that change in this equation, though. Specifically, this acceleration is going to have a different look than a normal. If we wanted to look at a centripetal force equaling a mass times a centripetal acceleration, our acceleration is going to change here. The reason why that acceleration changes is because this acceleration is being thought of as a circular acceleration here. We're going around in a circle, we're not just going in a linear line, which means that our centripetal acceleration is actually going to become v squared, the linear velocity squared, divided by r, the radius of the circle, okay? And what this means is that our equation, F equals ma, where this Fc can be thought of as a centripetal force or a sum of the forces making a centripetal force, that is going to equal m and then the centripetal acceleration, v squared over r. Okay, so that is our new F equals ma for centripetal forces here. What we also have, which can sometimes pop up in problems, is something known as a rotational period. Now, a rotational period, it's just a time. It's a period of time. And it's just the amount of time for an object to make one cycle of repeated motion. So if I'm spinning the foxtail like this, it's moving in a circle over and over and over and over and over and over again. But one cycle of it is from a starting position all the way around and then back to that starting position. It takes this foxtail some amount of time to make a circle, and that amount of time is the period. So the period is just the amount of time it takes for one cycle of a repeated motion. Periods happen with a lot of things. If you have a grandfather clock, a pendulum going back and forth has a period. A mass on a string has a period. The Earth orbiting the sun has a period of 1 year by our definition. So a period is just something that happens repeatedly over and over again. Now, for this period and this time, we use a capital T for it, and this can equal a few different things. We can say that this period is equal to 2 pi, because 2 pi is the angle of a circle, one cycle, divided by omega, the angular velocity of going around in a circular motion. And if you look at the units here, the units would be like radians over radians per second, which in the end just give you seconds, which is a time. So that's nice. We could also write this as 2 pi t over theta. If you knew an angle that something went through, like let's say it went through 10 revolutions, so it went through 20 pi radians, but you knew that time, you could work that out to find the period. Or if you knew the linear velocity of the object, you could say that this is going to be equal to 2 pi v over r. No, that's incorrect. I'm sorry. I got that backwards. 2 pi r over v. Haha. 2 pi r over v. And that makes sense there because my units up top are now meters over meters per second. Technically they're radians, but we don't care about radians when we're talking about linear. And then the meters cancel out and I get seconds in the end. So 2 pi r over v, which is just really the circumference of a circle divided by a velocity, which is just a distance over velocity, which is just a time, so a period there. So depending on what you have in a problem, maybe you're given the period and you can find a velocity. And the nice thing about this is if you have this velocity, then that means you can use it over here for our circular motion, our centripetal force equation. So that's just kind of what we're talking about for a centripetal force. It is an inward acting force. It is pointing inward on some sort of circular path. We can think about it as an object pulling back with some tension, but we can also think about it in different ways. If you're going through a loop-de-loop, we can think about centripetal force as, you know, if you're on a roller coaster, the roller coaster track is pushing back on you to keep you inside the loop. If you have something going in a horizontal arc like this, you can do the exact same thing with centripetal motion with everything held there like that. You can do this for, if you've ever been on that, I call it like a roundup ride at carnivals, where your back is against the wall and you start to spin and then the floor drops out from underneath you, but you're just magically held there. This idea takes place as well. Your centripetal force is pushing inward towards the center of that ride. And it also works if you're going like over the top of a hill. If you hit a hill fast enough, you'll kind of jump over it. But if you go over the top of a hill, this same idea can be applied there and what's going on. So we're going to take a look in the next video at how we can kind of think about some of the centripetal force. But this is what we're thinking about. We're just thinking about F equals ma. Our acceleration, though, has changed a little bit. It has become a centripetal acceleration, or a inward acting circular one. And we need to go back and think about how we add forces together to do that. Okay? So go check out the next video for some examples there, a little bit further analysis of what's going on with the F equals ma equation, how we can set up some problems. But that's what we're going to be doing. So take it easy. Have a good one.